right. So let's talk about some other factors that are at play in terms of filtration. And we can speak about things like our filtration fraction. So in order to think about filtration fraction, we first have to describe the renal plasma flow and then the GFR. So the renal plasma flow is about 625 milliliters per minute. And just to put some terms or to describe what this means, this is how much blood is coming into the glomerulus, okay? That is not necessarily how much is being filtered. This is why we have that efferent arteriole. So it would be wrong to think that all the blood coming into the glomerulus is being filtered. That's not the case. And that's what our filtration fraction is. It's how much of the blood that is coming to the capillary is actually being filtered across the glomerulus. And so we know that 625 milliliters per minute comes into the capillary via our afferent arteriole. We also know that about 125 milliliters per minute is filtered. So a small percentage of that, right? 20% of that is what actually makes it across our filtration membrane and ends up in our Bowman space as our filtrate. That winds up being about 180 liters per day. So a lot, right? Just lets us know that the kidneys are always filtering blood. And if we compare that to what's happening in the systemic capillaries, it's much, much higher. In the systemic capillaries, we had a filtration pressure of about 2 millimeters of mercury, whereas we just calculated out that across the glomerulus, our filtration pressure is about 16 millimeters of mercury. So a lot more force that's thrusting this plasma across our glomerular capillary, our filtration membrane. Another thing we can compare is our total filtrate per day. So whereas in the capillary system, we saw that we filtered 3 liters per day, right? 3 liters net ended up into our interstitial space. Here we're seeing 125 milliliters per minute, which is 180 liters per day. So a really drastic difference between how much filtration is happening across our capillary beds into our interstitial space, and how much filtration is happening here at the level of our glomerulus. So a lot more filtration. More of that fluid is making it across our filtration membrane and ending up in our Bowman space. Okay. And then going on here to really calculate our filtration fraction, it's basically our GFR divided by the renal plasma flow. And we know that GFR is 125 milliliters per minute. We know that our plasma flow is about 625 milliliters per minute. And so just doing that math here, so 125 divided by 625 is about 20%, so 0.2 or 20%. And this, the meaning behind this filtration fraction, again, is how much of my filtrate is actually making it across the filtration membrane and ending up in my Bowman space versus just being returned to the circulatory system via plasma. So we can see that here. The renal plasma flow, which is 625 coming in, and then only 125 actually being filtered, whereas 500 just simply returns to our vasculature. Okay, so about 20% of our blood coming into the kidneys is actually filtered across. Another thing we want to speak about here is the glomerular filtration, which is basically the filtered load. So how much of any substance that we can think about is actually being filtered across the glomerular membrane. And so to calculate our filtered load, it's our GFR, so the rate at which blood is being filtered, blood is moving across the filtration membrane, times the plasma concentration of whatever molecule we're trying to find the filtered load of. Okay, so X being whatever molecule we're trying to calculate the filtered load of. So small molecules are going to be filtered without any impedance or any blockage. They're going to be freely flowing across the glomerular filtration membrane. We know that large molecules, proteins, cells, they're going to stay behind. And so we can only calculate the filtered load of those small molecules that are freely filtered. So we would never be able to calculate the filtered load of something like proteins, right? Because proteins are not filtered. This is going to depend on the plasma concentration of the solute to begin with. So how much of our solute is present in the plasma, in the blood, and our GFR, which we know is pretty standard at about 125 milliliters per minute. So if we were to look at an example, calculating the filtered load for glucose, we simply multiply the GFR, which is 125, by the plasma concentration of glucose. And in a normal healthy adult, our glucose plasma concentration is about 100 milligrams per deciliter. And if we convert that to the accurate unit, right, so not deciliters here, but milliliters, so divide by 100, we get 1 milligram per milliliter. And so we simply multiply our plasma concentration, which is 1 milligram per milliliter, by our GFR, 125 milliliters per minute, and that gives us a filtered load of 125 milligrams per minute. In other words, if I have a normal concentration of glucose in my blood, 125 milligrams of glucose is filtered across my filtration membrane per minute, okay? Now, when you think about the amount of fluid that is filtered per day, only about 1.5 liters of urine is excreted, whereas 180 liters is filtered per day. Okay, back on our previous slide, we made that made that conclusion that 120 liters is filtered, so a lot of fluid being filtered here as compared to the capillaries. But if we think about our urine output is nowhere near 180 liters per day. Okay, that would put us into extreme dehydration. And so what this tells us is that most of the fluid that's filtered ends up being reabsorbed, right? More than 99% of what we filter across that filtration membrane ends up being reclaimed, as useful fluid, reabsorbed from the tubular space back into our capillaries in order to prevent those things like extreme dehydration. Okay, if we were to not have reabsorption, we would urinate 180 liters per day. That would be functionally a nightmare, right? Going to the restroom every minute, but also in terms of our body status, that would also be a nightmare, right? Extreme dehydration. What this also tells us is that a small change in GFR results in a large change in volume that's being filtered. And so in order to prevent that volume, to prevent us from losing that volume, we have to very tightly regulate our GFR. If GFR raises above 125 milliliters per minute, we end up seeing a large amount of volume being filtered and excreted, inappropriately. And so we want to keep GFR at 125. It's really important that we keep GFR at 125 to prevent extreme loss of fluid, which would happen if we raise GFR even slightly above that 125. Okay. So this just illustrates that tight regulation of our GFR. So within our mean arterial pressure, right? If we have a mean arterial pressure anywhere between 80 milliliters of mercury and 180 milliliters of mercury, we keep our GFR consistently at 125 milliliters per minute. And so this is the tight regulation of GFR. That means that if my mean arterial pressure, let's say it goes from 80 to 90, GFR stays at 125. If it goes from 90 to 120, GFR stays at 125. As long as it doesn't go above 180, which is where we start to get into extreme instances or extreme scenarios, we do our best, right? The kidneys, via some mechanisms that we're going to talk about in a minute, does its best to keep that GFR at 125, even in the face of a fluctuating mean arterial pressure, as long as it's not below 80 or above 180, okay? If we have an instance where our mean arterial pressure drops below 80, which again is something extreme, we're thinking about shock here, we're thinking about hemorrhage, we're thinking about severe dehydration, then we will just have to take the hit, right? That GFR will not be able to be sustained and it will drop below 125, okay? But again, these are extreme scenarios or extreme instances. Likewise, if we have our mean arterial pressure go above 180, let's say instances like chronic sustained hypertension, right? If you have someone with really high elevated blood pressures, this will also not be able to be regulated, and GFR will again take the hit and it will raise above 125. But for normal, healthy adults, we can fluctuate our blood pressure, fluctuate our mean arterial pressure anywhere between 80 and 180, and the kidneys will do everything that they can intrinsically and extrinsically to keep our GFR at 125. Okay. Okay, so really good question here for stimulants like caffeine that are diuretics. Do these affect GFR or is that something different? So stimulants like caffeine and any type of diuretic actually it affects the distal part of the tubule. So not necessarily the filtrate that's coming through, but how we fine tune that filtrate as it comes across the tubule. And diuretics in general, although they have different mechanisms, what they do is they prevent us from reabsorbing. So what we mentioned on the previous slide is that more than 99% of our filtrate ends up being reabsorbed. Diuretics manipulate the cells of the tubule and prevent that reabsorption from taking place. And so we lose that filtrate, whatever's been filtered out, instead of reabsorbing as much as we should, we lose some of that in the urine, and that's what a diuretic does. Either intentionally, which is, some diuretic medications like Lasix and so on, those will intentionally manipulate those cells, or unintentionally, which is some of the adverse effects of some herbs, medications, caffeine, as you pointed out. Okay. All right, let's look at the mechanism by which we keep this GFR constant. So I want you to have this in mind as we talk about these three mechanisms. These are the three mechanisms that helps to keep this 125, helps to keep us at this 125, even though our pressure can go up or go down.